And now, coming back to the concept of direction of contact force, so far we have done a few questions based on the ladder which is hinged. So now we are going to consider a question which is based on a ladder which is just resting on the wall. So there will be no hinge, which means there will be no hinge forces. So all we need to do is focus only on the normal reaction, which is always perpendicular to the contact surface. So here we go. The question is, a uniform ladder whose weight is 50 newtons and the length is 4 meters is placed against a frictionless wall, making an angle of 60 degrees with the ground. In part A, it states outline why the normal force acting on the ladder at the point of contact with the wall is equal to the frictional force between the ladder and the ground. Step 1, like always, is to draw the free body diagram of the ladder. So the first force should be the weight of the ladder, which is always acting downwards but passing through the center of mass of the ladder. So let's draw, let's say mg is the weight of the object acting downwards. Now, the ladder is resting on the ground as well as the wall, which means it is going to have two normal reaction. The ladder is resting on the ground, which means the ladder is going to experience a normal reaction coming from the ground, and this will be the direction. Let's say this is Ng. Ng stands for the normal reaction acting on the ladder coming from the ground. And the direction is important. Direction of normal reaction is always perpendicular to the contact surface. The contact surface in this case is the ground. Similarly, the ladder is resting on the wall. So ladder is going to experience a normal reaction coming from the wall. This arrow represents NW. NW would mean the normal reaction acting on the ladder but coming from the wall. And as you can see, direction of normal reaction is always perpendicular to the contact surface. Here, the contact surface is the wall. Now, apart from these three forces, Ng, Nw, and Mg, is there any other force still acting on the ladder? Yes, there is. Since the ladder is acting on the ground and ground is having a friction. See, the wall is frictionless, but the ground is having friction. So this point of the ladder is going to experience a friction force. And what will be the direction? That will be towards the right hand side. And why right hand side? Because imagine a situation if the ground were frictionless. If the ground were frictionless, then the ladder will have a tendency to move towards the left hand side. But since the ground has friction, that friction is going to oppose the leftward movement of the ladder, which means the direction of friction needs to be towards the right hand side. This will be F, the frictional force. Now, since the ladder is stationary, it is in equilibrium. So it is in linear equilibrium as well as rotational equilibrium. In linear equilibrium, we do the net forces acting on the object should be equal to 0, which means the total upward forces need to be equal to the total downward forces, and the total rightward forces need to be equal to the total leftward forces. So in this case, mg is the only downward force acting on the ladder, which will be equal to the ng, which is the upward force acting on the ladder. So let me write, if we are balancing forces along the y-axis, the equation will be ng will be equal to mg, and mg is the weight of the ladder, which is given to us as 50 newtons. So ng will be 50. Now we will balance the forces along the x-axis. So rightward force is friction and the leftward force is Nw. So both of them will be equal to each other. So let's write down F will be equal to Nw. And this is what we were supposed to prove in part A, which states that the normal force acting on the ladder at the point of contact with the wall, that is Nw. Nw should be equal to the frictional force between the ladder and the ground, that is F. So using the equation of linear equilibrium, we have established friction is equal to Nw, which was what we wanted to prove in part A. In part B, we need to calculate F. F is the force of friction acting on the ladder in the leftmost end. And we have already deduced that the friction value is equal to Nw. But we don't have the value of Nw. So this equation is not going to help us get the value of F. That is where we go to step number 3. Remember, step 1 was to draw the free body diagram. Step 2 was using linear equilibrium where we are balancing the forces. That's how we got these equations. Step number 3 is rotational equilibrium, where the net torque acting on the beam should be equal to 0. Now we have four forces acting on the ladder and we have to find torques of all the four forces. But before we do that, we need to establish a point about which we have to find the torque. And the trick to do that is we will consider that point about which maximum number of forces are passing. So if you see this point, the leftmost extreme, two forces are acting from this point. We have the frictional force and Ng. the normal reaction coming from the ground. If we take this leftmost point to be the hinge, if we consider this leftmost end to be the point about which we are finding the torques, then the torque of friction and torque of Ng will become equal to 0. So let us find torques of all the forces about the leftmost point. So let me write first of all the torque due to Ng will be equal to 0. Similarly, the torque due to friction will be equal to 0. Then let us try to find the torque due to mg, which is the weight of the object. The magnitude of torque is given by this formula R F sine theta. Now for mg, F, the value of F will be 50 newtons. R stands for the distance between the point and the force. So if I draw a dotted line from this point all the way till mg, this will be the value of R. And this length is actually half the length of the ladder. Length of the ladder is 4 meters. So this R will be equal to 2 meters. So torque due to mg will be equal to R, which is 2, multiplied by force, which is 50 newtons. Let's write it down. Multiplied by sine of the angle theta. Now, where is that angle theta? Theta is the angle between this length and mg. So, which means this angle is what we are after, theta. And how do we find that out? Since this angle is 60 degrees, now consider this as a right angle triangle where we have a 90-degree angle, a 60-degree angles, which means the third angle will be 30 degrees. Hence, we can say 30 degrees is the angle between mg and the r, which is the distance between the leftmost end and this point. So let's put theta as 30 degrees in this expression. So we will write sine 30. And if we simplify this, we will get 50 Newton meter as the answer. But this is only the magnitude. What about the direction? Now consider this leftmost end as the hinge point, for example. Then if you focus on mg, the weight of the ladder has a tendency to move the ladder in a clockwise direction. That is why the torque due to mg, let us write down the direction, it is clockwise. Now we are done with three torques. One torque is still left, torque due to nw. So let's write down the torque due to nw will be equal to Rf sine theta. R would be the distance from the leftmost point until this point. Now this entire length is equal to 4 meters. So torque will be equal to 4 multiplied by the force. Force in this case is Nw. So let's write it down. Multiplied by sine of the angle. The angle theta is this. So we need the angle between the ladder and Nw. And how much is this angle? This angle will be equal to 60 degrees. And why is that? Nw is horizontal and ground is also horizontal. So we have two parallel lines. So this angle, since it is 60 degrees, so this angle will also be 60 degrees because both of these are alternate angles. Hence, we can say the angle between NW and the ladder, it is 60 degrees, so which we will put here. So let's write down sine 60. Sine 60 is root 3 by 2. So if we simplify, we'll get 4 into NW into root 3 by 2, which when simplified gets us 2 root 3 times NW. This is only the magnitude. Direction will be anti-clockwise. And why is that? If you consider the leftmost point to be the hinge, then NW will have a tendency to move or rather rotate the ladder in an anti-clockwise direction. That is why torque due to NW will be anti-clockwise. And now, since the ladder is in rotational equilibrium, we will balance the clockwise torque with the anti-clockwise torque. So let's balance the two. So we will write 50 equals to 2 root 3 times NW. And let us make NW as the subject. We will get 50 divided by 2 root 3 as the value of normal reaction acting on the ladder but coming from the wall. And if we simplify this expression, we are going to get approximately 14.4 newtons as the answer. But in part B, we were supposed to find the value of friction F. For that, we use this equation, which we had found using linear equilibrium. Frictional value is equal to Nw, and Nw we have found as 14.4 newtons, which means the value of friction F will be also equal to 14.4 newtons, which is the answer for part B. In part C, the coefficient of friction between the ladder and the ground is given 0.4. We need to determine whether the ladder will slip. So how do we approach such questions? In part B, we have identified the actual value of friction which is acting on the ladder, which is equal to 14.4 newtons. And using the coefficient of friction, we can find the maximum friction which the ground can provide on the ladder. So let's write down the formula. The maximum friction acting on the ground. This is called the limiting friction. Now, if you recall, the formula for this is mu times the normal reaction. And which normal reaction do we take? There are two normal reaction. Now, since the friction is acting on the ground, so we are going to take Ng, the normal reaction which is coming from the ground. So in place of N, we will write Ng. The value of mu is given in the question as 0.4 multiplied by what is the value of normal reaction coming from the ground. And that we had already deduced earlier. Ng is equal to mg, which is equal to 50. So let's write down 50 over here. And if we simplify this, we are going to get 20 Newton as the maximum friction which the ground can provide. Now, all we need to do is just compare the value of actual friction with the maximum friction. So, actual friction was 14.4 newtons. Let me write it down. That is clearly less than 20 newtons, which means we can deduce that the value of friction which is acting on the ladder is less than the maximum possible friction which the ground can provide. That means the ladder is not moving, it is not slipping. Hence, the answer to this question is the ladder will not slip. So, let me write down the ladder is not going to slip since the value of friction which is acting on the ladder is less than the maximum possible friction. And that is how we solve such questions where the ladder is resting on surfaces, on the wall as well as the ground. The only difference compared to the hinged ladder was in case of a ladder which is just resting on surfaces, normal reaction is always perpendicular to the contact surface. But in case of hinged ladder, the normal reaction is called hinge reaction, and the direction of normal reaction is not fixed. It depends on the orientation of the ladder. But whatever the orientation, the hinge reaction always passes through the hinge point.